In this video, we're going to start chapter 6 of the chemistry textbook, which is on thermochemistry. All right, so what is thermochemistry? Well, typically in general chemistry, which is the category that this course and the textbook we're using fall under, the term thermochemistry is usually referring to the first law analysis of chemical reactions. The first law being the first law of thermodynamics. And that's actually what this entire chapter is going to be based on. In this chapter, we're strictly going to be looking at ways in which the first law of thermodynamics is used to analyze chemical reactions. And so if you watched the previous video, then you know that the first law is used to perform an energy balance on a system. In this case, in chemistry, the vast majority of the time, the system is defined such that all reactant and product substances of a chemical reaction are always contained within the system, and everything else in the universe is considered the surroundings. So with a first law analysis of a chemical reaction, you're analyzing the energy produced or consumed during the reaction based on the fact that over some time interval, the change in the total energy content within the system must be equal to the net energy transferred across the system boundary. And you can choose any time interval you want. No matter what the time interval is, the first law must always hold for the system. The energy balance must always be satisfied. Otherwise, that would imply that energy has been created or destroyed, which would violate a fundamental law of nature. Okay, and so again, when you're thinking about general chemistry, the term thermochemistry is typically referring to first law analyses of chemical reactions. But the broader meaning of the term thermochemistry is that thermochemistry is simply the thermodynamic analysis of chemical reactions. In other words, applying any of the laws, principles, or techniques of thermodynamics to analyze chemical reactions. For example, analyzing chemical reactions from the perspective of the second law of thermodynamics, which we're going to do later in the course when we discuss Gibbs free energy and the spontaneity of chemical reactions. But this type of analysis, this second law analysis, is also part of thermodynamics and therefore technically falls under the broader category of thermochemistry. But again, just so you don't get confused, in general chemistry, the way a textbook like this one is typically organized, it often appears as though applying the first law to analyze chemical reactions, just the first law is what's called thermochemistry, while second law analyses of chemical reactions, which involve entropy, Gibbs free energy, and spontaneity, are often presented under the heading of like chemical thermodynamics. Okay. So it says, every chemical reaction obeys two fundamental laws, the law of conservation of mass and the law of conservation of energy. We discussed the mass relationship between reactants and products in chapter 3. Here, we will look at the energy changes that accompany chemical reactions. Okay, so first of all, this law of conservation of mass and law of conservation of energy, these are laws of nature, not just laws of chemistry. Well, actually, let me clarify that statement. So in classical physics and classical chemistry, these are considered universal laws that apply in all contexts in the universe, not just in chemistry. However, when you move into more modern and deeper levels of physics, such as relativity, that's when the relation E is equal to mc squared comes into play. In that framework, it's more accurate to say that mass and energy together are conserved rather than just mass alone. Okay, so how do you know when you can just apply classical physics techniques as opposed to needing to apply the modern physics techniques? Well, the short answer is that classical physics and chemistry can be applied whenever quantum or relativistic effects are negligible compared to the scale of the system you're studying. So relativistic effects, Einstein's theory of relativity, become important when speeds approach the speed of light. And then quantum effects dominate when dealing with very small systems, such as atoms, electrons, and subatomic particles. Now, so, okay, but aren't we dealing with atoms and electrons and subatomic particles here in chemistry? Well, yes, but if we think about this from an energy perspective, so the idea is if the energies involved are small compared to nuclear energy scales, then classical analysis techniques are fine. In fact, they're appropriate. You don't want to use more complicated analysis techniques to analyze some system unless you have to. And so for ordinary chemical reactions that just involve rearrangements of electrons and chemical bonds, the energies are small compared to nuclear energies. In general chemistry, we're not dealing with changes in atomic nuclei. Okay, so therefore, from a classical physics and chemistry perspective, we say that the law of conservation of mass and the law of conservation of energy are universal laws of nature, not just laws that apply in chemistry. Okay, but obviously here we're focusing on chemistry. And so, again, we talked about in the previous video how the law of conservation of energy is applied in chemistry. The majority of the time in chemistry, the system is defined to, it's just including all of the reactants and products of a chemical reaction. That's the system. The system just isolates from the environment all reactants and products of a chemical reaction. That's it. And so to apply the law of conservation of energy to that system over any time interval, delta t, you're simply applying the first law of thermodynamics. Okay, but what about the law of conservation of mass? Well, in the previous video, we talked about how for this system definition used for chemical reactions, again, the system always encloses all reactants and products of the reaction. So let me bring in an example here. Here's the system, and contained within the system is some chemical reaction. The system encloses all of the reactants and all of the products at any stage of the reaction. Okay, and so we talked about how with the way that this system is defined, no mass ever crosses the system boundary. In other words, this is a closed system. The system will expand, contract, deform, move, do whatever it needs to do so that by the definition of the system, it always encloses all of the reactants and products of the reaction at any stage of the reaction. Okay, but still, even so, the law of conservation of mass still applies to this system. No matter what the system, over some time interval delta t, that this is a universal law of nature. The law of conservation of mass still applies. Now, maybe if perhaps you wanted to analyze this chemical reaction from some other perspective that's just related to mass, maybe you would redefine some other system. But it doesn't matter what the system is, the laws of thermodynamics, the conservation laws of nature, any of the laws of nature are always obeyed. So we can apply for this system here, the law of conservation of mass over any time delta t, which is just saying that over some time interval delta t, the change in the total mass contained within the system is equal to the mass that has come into the system over the system boundary over that time interval delta t minus the total mass that has left the system crossing the system boundary over that same time interval delta t. That's the law of conservation of mass. Okay, but again, because the system is closed, this particular system, that means that these two terms must be zero. The system's closed, that no mass crosses the boundary. So therefore, what that means is that over any time interval delta t, delta m is equal to zero, which is just saying that if delta m wasn't equal to zero, since these two terms are zero, delta m not being equal to zero would be implying that over some time interval delta t, mass has just kind of come from nowhere and come into the system or left the system. Mass has been created or destroyed. That can't happen under any circumstance. All right, so how is it ensured then that delta m in all scenarios, no matter what the delta t, delta m is always equal to zero? Well, that's the whole purpose of the requirement that a chemical equation must always be balanced. You don't have a proper chemical equation unless it's balanced. When you balance a chemical equation, you're simply applying the law of conservation of mass. That's it. So again, because the chemical equation inside of the system is balanced, that's what's ensuring that this is always true. Again, we're looking at this from this particular case of a system defined this way, to where it's always enclosing all reactants and products, and therefore these two terms are zero. Okay, now we're going to go ahead and read through this section 6.1 here, but we're not going to spend too much time discussing all of this because that was the purpose of the What is Energy video, which, if you're following along in the playlist, this should have not been, not the previous video, but 2 videos ago. Okay, so the nature of energy and types of energy. Energy is a much used term that represents a rather abstract concept. For instance, when we feel tired, we might say we haven't any energy, and we read about the need to find alternatives to non-renewable energy sources. Unlike matter, energy is known and recognized by its effects. It cannot be seen, touched, smelled, or weighed. Yeah, so that's what's tough about energy. As far as for people understanding conceptually what energy is that it's kind of abstract. You can't hold energy in your hand like you can mass. But now, like, forces are also kind of abstract. You can't hold forces in your hands either, but forces, I would say, aren't as abstract as energy. We can conceptualize a force. We can push on a wall and sort of visualize a force. Energy, I would say, is just a little more abstract than a force. And again, I go into this in a lot more detail in the What is Energy video. All right, so energy is usually defined as the capacity to do work. In Chapter 5, we defined work as a force times a distance, but we will soon see that there are other kinds of work. All forms of energy are capable of doing work, that is, of exerting a force over a distance, but not all of them are equally relevant to chemistry. The energy contained in tidal waves, for example, can be harnessed to perform useful work, but the relationship between tidal waves and chemistry is minimal. Chemists define work as directed energy change resulting from a process. Kinetic energy, the energy produced by a moving object, is one form of energy that is of particular interest to chemists. Others include radiant energy, thermal energy, chemical energy, and potential energy. Yeah, so, okay, if we think about the dimensions of energy, not the units of energy, the fundamental base dimensions of energy, all energy, no matter what form the energy is in, if it's the form of work, kinetic energy, potential energy, whatever, chemical energy, all energy comes down to it's a mass times a length squared divided by a time squared. All energy, no matter what the form. Okay, and so from these dimensions, there's 2 perspectives that you can view energy. You can view energy from the kinetic energy perspective and from the force times distance perspective, because, okay, kinetic energy is 1/2 times mass times velocity squared, right? So a mass times a velocity squared. So that's here. We've got a mass times a length per time, that's a velocity squared. So there's the kinetic energy, or the motion of mass perspective. When you think about energy, one of the main ways you think about what energy is energy is mass in motion. Okay, but now there's also the force times distance perspective. So a force we know is a mass times an acceleration. So mass times, and then acceleration is length per time squared. So there's a force, but now we still have an L here, so a force times a distance. Okay, so there's the force times distance, or the work perspective that you can view energy. Anytime you have a force acting over a distance, there's energy at play there. Specifically, that's more of an energy transfer. Work is an energy transfer, where kinetic energy is more of like an energy content. Anytime you push on something, a force goes over a distance, then you're adding velocity to a mass, or taking velocity away from a mass. Okay, but now you also want to think about, if you don't think about the idea of power, this can get confusing. Power is just energy per time. So power, you would add a it would be this, but then divide by time again. So mass times length squared per time cubed. And the idea of power is, so if I want to go from Los Angeles to Boston, well, I could walk there, right? Or I could fly there. In both cases, I've done the same amount of work. I've gotten myself from Los Angeles to Boston. The general idea is the same amount of energy was expended, whether or not I walked or I flew to get from Los Angeles to Boston. Yeah, I mean, I guess I'd be a lot more stressed out and annoyed. So my stress energy would be more. But as far as like forces over distances, it's the same amount of energy in both cases. But there's a difference, right? And the difference is that when you fly, that's a lot more powerful. That energy per time is a lot higher when you're flying versus walking. Okay, so now again, the idea is energy, fundamentally energy of something. So not an energy transfer, but the energy of something, energy content. It always comes down to its mass in motion. That's what energy is. It's mass in motion. And then now, okay, but what is potential energy then? Potential energy is very, very directly related to mass and motion, directly related to kinetic energy. Potential energy is just stored kinetic energy. If I've got water at the top of a mountain, it's not moving, but there is energy there in the sense that I could just tap into that water and here comes the mass and motion, right? Or like the chemical potential energy. It's that stored kinetic energy of the particles in gasoline. You just tap into it and boom, here comes out all this kinetic energy. Okay, now, but it's a little more complicated than this because we've got all of these different forms of energy. And so energy that's, thermal energy is that random energy of motion of particles, right? But you have the organized bulk energy of motion of like an entire mass as a unit. That's not thermal energy. We call that like bulk kinetic energy, bulk potential energy, bulk mass in motion. And then like mechanical energy are the types of energy that we're trying to obtain. That's bulk energy on the human size scale. That's like so our energy needs, right? The energy needs of society. We're trying to take all forms of energy out of the universe and convert them to mechanical energy. That's bulk energy of motion in unison on a human size scale. Okay, but all of these different forms of energy, radiant, thermal, chemical, they include potential here, but I would personally take potential out. Really, the fundamentals of what energy is, it's kinetic and potential energy. So it's energy of mass in motion or stored energy of mass in motion. And then there's really just work or forces over distances. That's how you transfer this kinetic or potential energy. Now you might say, well, okay, well, what about heat transfer? Well, heat transfer is more of just a category as well. That's the transfer of thermal energy. But still, when you're transferring thermal energy, you've got those particles colliding with one another, and that's forces over distances on the individual particles. So it's really just work, kinetic energy, and potential energy. The idea of thermal energy and heat transfer is just a matter of perspective. Because, for example, when you analyze biological processes, so the how things operate inside the human body, well, okay, we consider like in a lot of cases chemical potential energy to be like a thermal energy, that random energy. Whenever you spark gasoline, that random kinetic energy of motion comes out of the gas and does work, right? Well, but in a lot of biological processes, if you have a molecule that has all this chemical potential energy, well, what's happening is the biological system is breaking those bonds, and then a particle comes out fast and it locks into place somewhere else. It kind of forces a valve to open. Well, that's not thermal energy. That's mechanical energy. At least from the perspective of the small biological system, that's at the size scale of the biological system. That's mechanical energy. So it's really energy. It's fundamentally comes down to its mass in motion, stored mass in motion, and forces over distances that transfer this mass in motion or stored mass in motion. And so these different forms of energy are just different categories that we put energy into just to make it easy for discussion and study and communication. Okay, so radiant energy or solar energy comes from the sun and is Earth's primary energy source. Solar energy heats the atmosphere and Earth's surface, stimulates the growth of vegetation through the process known as photosynthesis, and influences global climate patterns. So yeah, radiant energy can be kind of confusing because they're talking about electromagnetic radiation, But we know that, so here's an electromagnetic wave. We know that electromagnetic waves or light is considered massless. So from the classical perspective, so we're not thinking about E is equal to mc squared. This is not a mass in motion. A photon is not a mass in motion. It's massless. So how is this energy? Well, because electromagnetic waves come from charged particles that are accelerating and decelerating, right? And what they do is that they transfer this energy of motion of charged particles from one charged particle to another. An electron, let's say, emits a photon, and that gets transferred to some other electron somewhere else. So I guess technically you could look at a photon as more of an energy transfer device, but still, it's the energy of the photon is it's associated with the mass and motion of the particle it came from, the charged particle it came from, and therefore it's going to transfer that energy to some other charged particle. Okay, thermal energy is the energy associated with the random motion of atoms and molecules. In general, thermal energy can be calculated from temperature measurements. The more vigorous the motion of the atoms and molecules in a sample of matter, the hotter the sample is and the greater its thermal energy. However, we need to distinguish carefully between thermal energy and temperature. A cup of coffee at 70 degrees Celsius has a higher temperature than a bathtub filled with warm water at 40 degrees Celsius, but much more thermal energy is stored in the bathtub water because it has a much larger volume and greater mass than the coffee, and therefore more water molecules and more molecular motion. Yeah, so thermal energy, again, this is still just masses in motion. Thermal energy really is just kinetic energy at a fundamental level, but it's just a category that we as humans use to describe this type of energy because it's different than the motion of the kinetic energy of a hammer. It's this unorganized kinetic energy. It's in a different form. Okay, but they're wanting to point out here, and this is important to note, that you can't just simply look at a temperature reading and say that, okay, this substance has a higher temperature than this other substance, so it has a higher amount of thermal energy. Meaning, if you took a system and you said, you put that system around some substance, and that substance was at a certain temperature, and you said, okay, now here's the thermal energy. You took a snapshot, took a picture, and you said, okay, at this moment in time, the total thermal energy of this substance is this. Then you had some other system with some other substance, and that substance was at a lower temperature than the first substance, and you said, okay, here's at this same moment in time, here's the thermal energy contained within this system. You can't just say that, oh, well, the substance with the higher temperature has a higher total amount of thermal energy contained within the system than the substance at the lower temperature. No, because it depends on the amount of substance. Temperature is an intensive quantity, meaning that it's a physical property that doesn't depend on the amount of substance or the size of the system. So really what you would need to say is that for two separate substances to where the total amount of the substance, the total mass of the substances is the same, then you can do a direct comparison of the temperatures to say, okay, if this substance is at a higher temperature than this substance, then it has a higher total amount of thermal energy than the substance at the lower temperature. Again, the thermal energy, you're just adding up all of the kinetic energies of all of the particles, of the random motions of all of the particles. And you can see from that perspective that's the reason why if you have a cup of coffee at 70 degrees Celsius and a bathtub filled with warm water at 40 degrees Celsius, well, when you're thinking about the total thermal energy of these two systems, well, when you add up all of the kinetic energies of all of the particles of water, even though the average of those kinetic energies is less than the average of the kinetic energies of the cup of coffee, the total kinetic energy is still going to be more here. Yeah, the average is less because you're dividing by, when you divide by n, the total number of particles, that's a larger number. But if all you're looking at is the total, you're not taking the average, well, then there's going to be more thermal energy here. Okay, chemical energy is stored within the structural units of chemical substances. Its quantity is determined by the type and arrangement of constituent atoms. When substances participate in chemical reactions, chemical energy is released, stored, or converted to other forms of energy. Yeah, so chemical energy is it's a potential energy. So it's a stored kinetic energy, energy that's stored in the bonds of molecules. The bonds of molecules, the bonds between atoms of molecules, or even if it's not a molecule, just like bonds between chemical bonds between atoms. Because it takes you have to apply a force over a distance you can think about push atoms together and fix them into these bonds. They get fixed. And so now what you've got is this stored kinetic energy to where if you release the chemical bond, the result could be that the products, so like if you're changing bonds, breaking bonds, creating new bonds, that's a chemical reaction. The result of the chemical reaction could be that the products have a higher average kinetic energy than the reactants. You've released kinetic energy from the chemical potential of the bonds, or it could go the other way. It could be, we're going to see how it could be that the products have a lower average kinetic energy than the reactants. So it's not just the case that how we think about for gasoline, you've got all this stored kinetic energy in the chemical bonds. If you can break those bonds, now everything's going to come out, all the particles are going to come out with higher kinetic energies. Not necessarily. It could go the other way. Okay, now potential energy is energy available by virtue of an object's position. For instance, because of its altitude, a rock at the top of a cliff has more potential energy and will make a bigger splash if it falls into the water below than a similar rock located partway down the cliff. Chemical energy can be considered a form of potential energy because it is associated with the relative positions and arrangements of atoms within a given substance. So, yes, potential energy, again, I wouldn't put potential energy into the same category as chemical energy, thermal energy, radiant energy, electrical energy. These names are just categories that we, sort of shells that we put different forms of energy into for communication purposes, labeling purposes. Potential energy is more of directly related to kinetic energy. Potential and kinetic energy are first cousins. Potential energy is stored kinetic energy. And like it says here, when you think potential energy, you always want to think position. You cannot write any definition of potential energy without using the term position. So it's stored kinetic energy of a mass as a result of that mass's position in some system relative to a reference point. So, you have water at the top of a mountain. Well, how much potential energy does that water have? Well, it depends on what the reference point is. If you're in some town that's midway down the mountain and you want to use that water for some purpose, well, its potential energy is the height of the water relative to that town, not sea level. But if you have some other town at sea level and you want to tap into that water, well, its potential energy is based on its height relative to sea level. You see, chemical potential energy, it's based on the stored kinetic energy of the atoms, the particles, and it's based on the positions of the atoms within the bonds. Okay, all forms of energy can be converted, at least in principle, from one form to another. We feel warm when we stand in sunlight because radiant energy is converted to thermal energy on our skin. When we exercise, chemical energy stored in our bodies is used to produce kinetic energy. When a ball starts to roll downhill, its potential energy is converted to kinetic energy. You can undoubtedly think of many other examples. Although energy can assume many different forms that are interconvertible, scientists have concluded that energy can be neither destroyed nor created. When one form of energy disappears, some other form of energy of equal magnitude must appear, and vice versa. This principle is summarized by the law of conservation of energy. The total quantity of energy in the universe is assumed constant. Yeah, so the law of conservation of energy comes from this strong conclusion that the science community has universally agreed upon. And remember that there's no conclusion in science that's ever a perfect fact. The most factual you can get in science is when something becomes a theory, right? Atomic theory. The fact that matter is made up of these indivisible units called atoms. That's still atomic theory. And it becomes a theory whenever that there's so much universal evidence that points to the truth of this theory, to where people have just sort of universally agreed upon the idea that we're going to sort of assume that this is fact, even though nothing is considered to truly be a fact in science. But it's just that there's so much evidence to support, at least currently up to the year 2026, that energy cannot be created or destroyed. And same with mass. Okay. All right, so it says often the energy changes that take place during chemical reactions are of as much practical interest as the mass relationships we discussed in chapter 3. For example, combustion reactions involving fuels such as natural gas and oil are carried out in daily life more for the thermal energy they release than for their products, which are water and carbon dioxide. Yeah, so doing thermodynamic analysis of chemical reactions is very useful. Almost all chemical reactions absorb or produce energy, generally in the form of heat. It is important to understand the distinction between thermal energy and heat. Heat is the transfer of thermal energy between two bodies that are at different temperatures. Thus, we often speak of the heat flow from a hot object to a cold one. Although the term heat by itself implies the transfer of energy, we customarily talk of heat absorbed or heat released when describing the energy changes that occur during a process. Thermochemistry is the study of heat change in chemical reactions. Okay, so let me bring up a control volume here. Okay, so here's the system that we consider for the analysis that we perform in chemistry. And again, in the majority of cases, the system is defined such that it encloses all of the reactants and products of a chemical reaction. So this could be any chemical reaction. Here's some different types of chemical reactions we've discussed up to this point. Okay, and so again, as we talked about in the previous video, because of the way this system is defined, it's a closed system. Therefore, the only types of energy transfers that occur across the system boundary are in the form of heat or work. And then, as far as the energy content contained within the system, the changes in the bulk kinetic energy and the bulk potential energy are typically negligible for chemical reactions. Therefore, the only significant change in the energy content, the total energy content contained within the system over some time interval delta t, is the change in the internal energy contained within the system, right? So that's why when you're studying a chemical reaction from the perspective of the first law, you'll typically just see that the first law written out as delta U is equal to Q plus W. The change in the total amount of internal energy contained within the system is equal to the net total amount of heat transferred across the system boundary plus the net total amount of work transferred across the system boundary. And like all of this is over the same time interval delta t. Okay, and so in the previous video, we talked about the exact meaning of energy transfer across the system boundary in the form of heat. Okay, and so remember, any heat transfer that's taking place strictly within the system or strictly outside of the system is not relevant to the first law energy balance. We're strictly looking at heat transfer. So here we're strictly looking at heat transfer that occurs across the system boundary, either into or out of the system. So this is positive if going into the system, negative if coming out of the system. And really, this is the same idea with any of the energy transfers contained within the first law, work or mass transfer. It's strictly these energy transfers are occurring across the system boundary. Okay, but physically, heat transfer is the transfer of thermal energy. To where thermal energy, again, like we just talked about, we really first learned about thermal energy when learning about the kinetic molecular theory of gases, to where the temperature of a gas is proportional to the average kinetic energy of the gas particles, where those kinetic energies correspond to the random microscopic motion of the particles. Well, we haven't officially discussed this yet in detail, but the same general idea applies to solids and liquids. Any substance, no matter what state it's in, has thermal energy associated with it, which arises from the microscopic motion of its particles. The average kinetic energy of these microscopic motions is directly related to the temperature of the substance. Okay, so that's exactly what heat transfer is. It's the transfer of thermal energy between two different substances or between different regions of the same substance down a temperature gradient. So in other words, there must be a difference in temperature, a delta T. Q is a function of a delta T. There must be a temperature gradient present in order for heat transfer to occur. So if a temperature gradient exists, then heat transfer or the transfer of thermal energy will take place either between different substances or within the same substance. Okay, now it says here how this can sometimes be confusing because in casual conversation, you might hear the term heat used to describe an energy content contained within a system. In other words, the term heat might be used in a way similar to how we talk about internal energy. For example, at a given moment in time, if you take a snapshot of a system, there's a total amount of internal energy contained within the system, to where a portion of this internal energy is in the form of the random kinetic energies of the particles of mass contained within the system. And sometimes instead of referring to this energy, like remember, internal energy also includes, don't forget, internal energy also includes like chemical potential energies, but thinking about the random kinetic energies of the particles of mass, where correctly this should be referred to as thermal energy. Sometimes you'll hear in casual conversations, people will refer to this as heat content, the total amount of heat content in a system or in a substance. And again, what's technically being referred to in this case is thermal energy content within the system or within some mass. Okay. However, from a scientifically precise standpoint, that there is no such thing as heat content. There's thermal energy contained within a system. And the term heat is just referring to any process to where a transfer in thermal energy occurs, either within the same substance or between different substances. And if this transfer in thermal energy occurs across a system boundary, then that's the amount of this energy transfer in units of energy is going to correspond to this term here, the net amount of heat transferred. Add up all the heat transferred over some time delta T, the amount of heat transferred into the system, and then subtract out the amount of heat transferred out of the system, the amount of thermal energy transferred across the system boundary, and this net sum total goes here. Right, so saying that there is heat content within a system would be similar to saying that there's work content, a certain amount of work contained within a system, which doesn't really make sense, right? And now, this last sentence says that thermochemistry is the study of heat change in chemical reactions. And so, again, this statement here is probably using the term thermochemistry in the sense of applying the first law of thermodynamics to study chemical reactions, even though more broadly speaking, thermochemistry can be thought of as the application of just general principles and techniques of thermodynamics, the general subject of thermodynamics, to the analysis of chemical reactions. Okay, so it says to analyze energy changes associated with chemical reactions, we must first define the system or the specific part of the universe that is of interest to us. For chemists, systems usually include substances involved in chemical and physical changes. For example, in an acid-base neutralization experiment, the system may be a beaker containing 50 milliliters of hydrogen chloride to which 50 milliliters of sodium hydroxide is added. The surroundings are the rest of the universe outside the system. There are three types of systems. An open system can exchange mass and energy usually in the form of heat, with its surroundings. For example, an open system may consist of a quantity of water in an open container, as shown below. So if the system is the entire interior volume of this flask, then, and you've got water here, then this would be considered an open system because water vapor can vaporize and leave the system, cross the system boundary here. Or you could have water vapor come in here and potentially condense into the liquid. So since mass can cross this system boundary, this is what's called an open system. With open systems, the idea is you can have any kind of energy transfer, mass transfer, heat transfer, or work. Yeah, so I mean, if there's a temperature gradient between the environment and the water, you can have heat transfer, right, across the walls of the flask. Now, it says if we close the flask so that no water vapor can escape from or condense into the container, we create a closed system, which allows the transfer of energy. It says heat. I don't know why they're just saying heat, but not mass. Yeah, because a closed system, just there's no mass transfer across the system boundary, but there can be heat or work transfer. So in this case, again, with the system being just the interior volume of the flask, well, if the flask is closed here, well, now no water vapor can enter or leave the system. No mass can enter or leave this system. So it's a closed system. But obviously, heat can still be transferred across the walls of the flask if there's a temperature gradient between the system and the surroundings. But yeah, here, technically, if the system were the interior volume of this flask, then no work could be done in this case because the boundaries of the flask, the inner walls of the flask, can't move, right? In order for work to take place at a system boundary, the system boundary has to move, either as a rigid body or expand or contract or deform. But I guess I'm just saying that so, okay, let's say you instead made the system to be just enclosing the water in the container. That's it. But you didn't include the water vapor up here. Well, okay, if the temperature changes, then you're going to get a higher vapor pressure up here. So you get a higher pressure on the water body, and it will be a slight change in volume of the water because liquids and solids are much less compressible than gases. But still, that even that small change in volume, that's going to be a change, a movement in the surface boundary that's occurring under some pressure. So that would be work. But even in that case, the system that's just enclosing the water here would be a closed system. Okay, but now it says by placing the water in a totally insulated container, we can construct an isolated system, which does not allow the transfer of either mass or energy. So yeah, in an isolated system, there are no energy transfers. There's no heat, no work, no mass transfer. Okay. The combustion of hydrogen gas and oxygen is one of many chemical reactions that release considerable quantities of energy. So, okay, you've got H2 gas reacting with O2 gas to produce liquid H2O. And it's saying that in this process, there's a release in considerable quantities of energy. In this case, we label the reacting mixture, the hydrogen, oxygen, and water molecules, the system, and the rest of the universe, the surroundings. Because energy cannot be created or destroyed, any energy lost by the system must be gained by the surroundings. Thus, the heat generated by the combustion process is transferred from the system to its surroundings. All right, so let's think about exactly what they're saying here. We've got this reaction, the combustion of hydrogen gas and oxygen to produce H2O. But again, they're saying that as this reaction takes place, a considerable amount of energy is released in the process. And really, they're specifically referring to thermal energy. What they're ultimately saying is that as this reaction takes place, so as H2 molecules combine with O2 molecules, and a chemical reaction takes place, bonds are broken, atoms are rearranged, new bonds are formed to produce H2O molecules, the resulting H2O molecules have a larger average kinetic energy, have larger kinetic energies on average than did the initial H2 and O2 molecules. That's exactly what they're saying here. Now, you might look at this and be a little confused because the product here is written as liquid H2O. Wouldn't the H2O coming out of a combustion process be gaseous? Yes, it would. It definitely would. And this is something I'm going to talk about in more detail in either the next video or two videos from now. But here's the idea. Here's what they're saying. So let's bring up this system again here and add this reaction to the system. All right. So before the reaction begins, the system encloses, you can think about this as the system encloses a gas mixture of H2 and O2 gas. And at this point, when we're just looking at the reactants, we want to imagine that this system of reactants has already settled into an equilibrium in the sense that that there's no temperature gradient within the system. There's no pressure gradient, no concentration gradient. And then furthermore, the temperature and pressure of the gas body, of the reactants, are also in equilibrium with the surrounding atmosphere. So the temperature of the gas is the same as the temperature of the surrounding atmosphere. Same with the pressure of the reactants. Okay, so now the reaction begins, the combustion process begins. And yes, for essentially all combustion processes in which H2O is produced, the H2O will initially form in the gaseous state. So, from a simplified perspective, if we think about this reaction in stages, let's hypothetically imagine a moment in which the reaction has gone to completion, and we'll assume that the amount of reactants are present in the stoichiometric amounts. So there's no limiting or excess reagents. Okay, so the reaction has gone to completion. Now we're left with only H2O, but let's imagine this as the instant in which the reaction has just completed. Again, this is a simplified conceptual picture of the reaction. And so at the instant the reaction has gone to completion, the H2O will be in the gaseous state. And it will be the case that this gaseous water, this body of gaseous water, will have a higher average kinetic energy of its gas particles than the average of the kinetic energies of the particles in the initial gas body reactant mixture. Okay, and so if the average kinetic energy of the particles in one substance is higher than that of another substance, then we know that the temperature of that substance with the higher average kinetic energy must be greater, right? Must be higher. So the temperature of the gaseous H2O must be higher than the temperature of the reactants. The temperature of the gaseous H2O body at the instant after the reaction has completed must be higher than the temperature reading of the reactant gas body mixture of H2 and O2. Okay, but what was the temperature of the reactants? Well, that was essentially the temperature of the surrounding environment, right? Since the system was initially in thermal equilibrium with the surroundings. So right after the reaction is complete, the temperature of the gaseous H2O is higher than the temperature of the surrounding environment. And as a result of this temperature difference between the system and the surroundings, heat transfer occurs. Specifically, heat transfer occurs down the temperature gradient, which means in this case, heat is transferred from the system to the surroundings. In practice, this heat transfer will occur through the mechanisms of conduction, convection, and radiation. Okay, and so what they're illustrating here is that this heat transfer occurs between the system and the environment until the system returns to thermal equilibrium with the surroundings. Okay, now something else to note is that in many cases, if we think about the surrounding environment, such as the air in a room or the outdoor atmosphere, the surroundings are often treated as a thermal reservoir or heat bath, which means that the thermal energy added to or removed from the surrounding environment by a chemical reaction has a negligible effect on the temperature reading of the surroundings, the surrounding environment. And the reason for this is that the surroundings are typically much larger in scale than the system. So the energy transferred during the reaction is negligible compared to the total thermal energy contained in the environment. Okay, but now we can also think about the surrounding pressure conditions here as well. If the reaction is simply taking place outdoors or in a laboratory atmosphere, then the pressure throughout the entire course of the reaction will essentially be atmospheric pressure, right? That wouldn't necessarily be the case if the reaction were taking place inside of a closed chamber or some other controlled device, but it's just something to keep in mind. But okay, so the idea is that, so you've got this gaseous H2O vapor immediately after the reaction has completed. We're thinking about this hypothetically as if all of the reactants have been consumed, and now we have just like immediately after the reaction is completed, this is a combustion reaction. You've got this gaseous H2O body, pure gaseous H2O, which is initially at a higher temperature than the surrounding environment. Well, what's going to happen is that this gaseous H2O will eventually come into thermal equilibrium with the surroundings. And since the surroundings are acting as a thermal reservoir or heat bath, then the temperature of the surroundings is not going to change much at all relative to where it started before the reaction even began. Well, okay, so if that temperature is around room temperature, this ambient temperature is around room temperature, then the final equilibrium phase of the gaseous water is going to be liquid water, right? Assuming, like normal atmospheric pressure as well, just a typical atmospheric pressure. And so that's why the final product here is listed as liquid H2O, not gas H2O. Okay, and so now, but they also reference here how energy is released as one of the products in this reaction. And more specifically, what they're saying is that the products of this reaction initially, right after the reaction is complete, have a higher average kinetic energy than the reactants. Now, okay, if we take a look at this sentence again here, it says, because energy cannot be created or destroyed, any energy lost by the system must be gained by the surroundings. I don't really like this sentence because I don't think the authors are being completely precise in their wording. Because to me, it almost sounds like they're implying that we start off with pure reactants, and then when the reaction proceeds, it's almost as if energy is somehow being added to the system. What I mean is, so if you write the first law here for this system, the way this sentence is worded, it's almost like they're implying that this energy here would fall under the category of a positive delta U. Energy has been added to the system as a result of this chemical reaction taking place. And therefore, in that sense, since energy can't be created or destroyed, then there must have been some energy transfer across the system boundary to the system to account for this addition of total energy content within the system. But that's not really the correct way to think about it. Because in actuality, if we consider a delta T that goes, it starts at time zero is when you just have pure reactants, and then the final time is all the way to the end where you just have pure liquid H2O. From that perspective, from the perspective of that delta T, that change in time, that time interval, the change in internal energy here is actually negative. Going from time T0 to T final, the total internal energy contained within the system decreases. So let's think about this. So, okay, this energy here, this energy coming out of this chemical reaction is not added to the system. This is not an increase in the internal energy content contained within the system. All that's happened here is you've had a transfer of internal energy strictly within the system, not across the system boundary. You've had internal energy transferred between chemical potential energy and thermal energy within the system. That's it. You've gone from the chemical potential energy of the H2 and O2 gas molecules to the increased thermal energy of the gaseous H2O. So at the instant that the reaction is complete and you have this gaseous H2O, all that's happened is you've had a transfer of internal energy strictly within the system, which is not applicable to the first law. You just had chemical potential energy change forms to a thermal energy. That's it. And just because energy changes form within a system, that doesn't mean that energy must necessarily be transferred across the system boundary. There is no requirement like this in thermodynamics. You can absolutely have a system that's in equilibrium with respect to its surroundings, meaning that no energy transfers are occurring across the system boundaries, while at the same time, energy transformations and microscopic energy exchanges are occurring internally within the system. And so, more specifically, more precisely, what's happening here is that as a result of the reaction, chemical energy is converted into thermal energy initially within the system. And then as a result of this conversion, what you end up with is a temperature difference between the system and the surroundings, which therefore results in heat transfer occurring between the system and the surroundings. Okay, so how exactly do these processes apply with respect to the first law? Well, okay, so let's continue to look at this from a simplified perspective in stages. So we can analyze the first law. We can apply the first law with respect to any time interval, delta t, that we want. The first law has to hold for any time interval. Okay, so first, let's consider the process of going from, let's consider the delta t that corresponds to going from just pure reactants to right after, the moment after the reaction is complete. So you just got this gaseous H2O. Well, okay, so over this time interval, the delta U here is going to be 0, right? Because yes, the internal energy within the system has changed form, going from chemical energy to thermal energy, but that transformation occurred entirely within the system. The total energy contained within the system hasn't changed over that time interval. And during this same time interval, no heat or work interactions took place across the system boundary, so the equation balances. Okay, now, well, what about the time interval going from the initial high temperature gas H2O to liquid H2O? Well, during this interval, there is heat transfer out of the system. And let's just hypothetically say that there's no work transfer. Okay, so over this time interval, for the first law to balance, it must be the case that the total energy content, the total internal energy content contained within the system decreased, because you have a negative Q here, so you need a negative delta U here. And yes, this makes sense, because over this time delta T, the thermal energy content contained within the system decreased. So there was no change in chemical potential energy that's also contained within internal energy, because you just had gaseous H2O going to liquid H2O. So the only type of internal energy that changed was the thermal energy, and the amount of thermal energy contained within the system decreased. Okay, now let's apply the first law for the time interval going from the initial pure reactants all the way to the final just pure liquid H2O products. Now, what's interesting about applying the first law over this time interval is, so, okay, at the initial time, before the reaction started, we had the reactants at some temperature, and at the final time, after everything came back to equilibrium with the surroundings, we have liquid H2O at essentially that same temperature. So even though heat has been transferred out of the system during this particular delta T, the initial and final temperatures of the system are the same. And so because of this, the heat transfer over this time interval from this perspective can't be interpreted simply as a decrease in the total thermal energy content of the system. So then we ask, well, what form of energy within the system actually decreased as a result of this heat transfer? We know it's going to be something related to internal energy. So what form of internal energy decreased over this particular time interval as a result of this heat transfer out of the system? Well, if it's not thermal energy, well, then there's only one other form of internal energy, that's chemical potential energy. Going from a mixture of H2 and O2 gas to H2O, you have a decrease in chemical potential energy, right? So even though the thermal energy of the system ends up at essentially the same level as it started, the chemical energy stored in the molecular bonds has decreased. And also, just to note, you might be wondering, well, how can we say that the thermal energy content hasn't changed going from reactants to products here, strictly based on saying that the temperatures of the two states are the same? Well, remember, we can do this. We can strictly compare thermal energies with respect to temperature if the amounts are the same, if the total mass is the same. And when it comes to conservation of mass, you're going to have the same total mass here as you have here. Okay, and so again, for this delta T going from just a pure reactants all the way to the final liquid H2O products, it's this change in chemical potential energy. It's this decrease of chemical potential energy contained within the system that's leading to the heat transfer out of the system. So this is similar to what happens when you burn gasoline. The chemical energy stored in the fuel molecules is no longer present in the products, like CO2 and H2O. That chemical energy has been converted into other forms of energy, and most of it ultimately leaves the system as heat. Okay, and now you might also be wondering, particularly if you watched the previous video, why aren't we discussing the fact that when going from this initial mixture here of gases to products, to the liquid H2O, the system volume clearly decreases. And so if there's an external pressure from the surroundings, from the surrounding environment, then wouldn't there be PV work involved, pressure volume work involved? And yes, there absolutely would be. And so to be technically precise with respect to the first law here, I shouldn't have been stating that we're going to assume that the work term is zero. To state that this work term would be equal to zero, it needs to be the case that this reaction is taking place, like in space or in a vacuum, to where there is no environmental pressure. Otherwise, for any of the scenarios we just discussed, going from the reactants to gaseous H2O, or going from the gaseous H2O to liquid H2O, or even going from the initial pure reactants all the way to the final liquid H2O, if the system volume changes at all, and during this change there's any external pressure acting on the system, then PV work is involved and would need to be accounted for as a work energy transfer in the first law. But for now, just in this opening section here, we're mainly just focusing on heat transfer, the transfer of thermal energy associated with chemical reactions. We'll discuss PV work, which is closely related to enthalpy, in a later section. Okay, and so it says this reaction is an example of an exothermic process, which is any process that gives off heat, that is, transfers thermal energy to the surroundings. All right, so any chemical reaction for which, as a result of the reaction taking place, there's heat transfer, that there's a net heat transfer out of the system, is referred to as an exothermic reaction. So remember, the system we're talking about here is one that encloses all of the reactant and product substances of a chemical reaction. And as far as the details of the physical setup, for example, whether the reaction occurs inside of a container, whether there is PV work involved, or any other mechanical details, those factors don't affect the definition of exothermic or endothermic. The only thing that matters for this definition of an exothermic or an endothermic process, and notice how also these terms exothermic and endothermic are not strictly associated with chemical reactions either. They're just talking about exothermic processes, endothermic processes. These terms are strictly in reference to whether there is a net amount of heat transfer, a net amount of heat transfer. So you add up all the heat transfers going in and out. These terms are strictly in reference to whether there is a net amount of heat transfer into or out of the system. If thermal energy leaves the system, meaning heat is transferred out of the system, then the reaction or the process is called exothermic. And so the reaction we just looked at, right, the process we just looked at was an exothermic process. Okay, now the opposite of an exothermic reaction is an endothermic reaction, in which heat has to be supplied to the system. And they give an example here of a chemical reaction that is endothermic. So going from reactants to products, heat is transferred into the system. That's why this reaction here is endothermic. All right, so endothermic reactions can sometimes be a little bit confusing to think about at first. And I think that this is partially because exothermic reactions are more familiar to us in everyday life through things like fires, combustion, explosions. But with an endothermic reaction, the same general thermodynamic ideas apply as what we just went through with an exothermic reaction example. So in an endothermic reaction, the products, so right after the reaction has complete, so that the instant after the reaction has taken place, the products are going to initially have a lower average kinetic energy of their particles than the reactants had. In other words, the products are at a lower temperature than the reactants, to where the temperature of the reactants is the temperature of the surroundings. So at the instant in which the reaction takes place, the products are at a lower temperature than the surroundings. And so because of that temperature difference, heat transfer occurs, in this case, from the environment into the system. And that's what they're illustrating here. You can see that the surface of the glass vial is cold. And that happens because the products are at a lower temperature than the surrounding environment. So in order for the system to return to thermal equilibrium with the surroundings, essentially back to room temperature, the system needs to absorb heat from the environment. And in the example here, that this is illustrated in that the system is absorbing heat from the flame. Okay, so in the next video, we're going to go over more specifics about the first law and how it works. A lot of the core ideas here we've already been discussing in this video and the previous video, but there are some additional details and new concepts in this next section that we'll want to cover as well.